Hi everyone! In this video we're going to use the concept of transformations in order to graph more logarithmic functions. And we'll compute an example where we complete the function table for a logarithmic function using evaluating rather than the method used in the last video, which was to just reflect an exponential function. So our original function is f of x equals log base 10 of x, or in other words, we usually just write it log of x. And I want to create my function table first. So if I plug in 1 over 100, what do I get for f of x? Well, I have my scratch work down here. That's going to be log of 100, and I'm looking for y. If I rewrite this as an exponential expression, I take the base of my log, which is 10, raise it to the y power, and say that equals 1 over 100, because that's what's going inside of the log function. This is how I convert from logarithmic to exponential form. So what does this tell me that y has to be? I'm trying to figure out 10 to the what equals 1 over 100. If you notice, 1 over 100 is the same as 1 over 10 squared. So y must be negative 2. 10 to the negative 2 is 1 over 10 squared, which is the same as 1 over 100. So f of x, when x is 1 over 100, is negative 2. Log of 1/10, if that's my y, then I'm looking for the y value. That makes 10 to the y equal 1 over 10. So what's that going to be? That says y has to be negative 1. So log of 1/10 is negative 1. Log of 1 is going to be the value that I do. 10 to the y equals 1. Well, in order to get 1, I have to raise to the 0 power. So y equals 0 here. And the rest of these points, maybe I could possibly do one more. So log of 10 equal y is saying 10 to the what equals 10. So in that case, y equals 1. If I want to get some more values, I'm going to need my calculator. So say I want log of 2. I can literally just press log of 2, and that gives me 0.301. Maybe I want log of 5. That's going to be 0.69. I'll round it to 0.699. And log of 8 is 0.903. So now I've got enough points I can actually graph this function. So 1 over 100 for x is very, very small. So that's going to be around that point. 1/10 for x might be somewhere around here. That's negative 1. And then finally, when x is 1, I'm at 0. When x is 2, we saw here that we're at 0.301. So 0.3 is probably around here. When x is 5, my y value is around 0.9. So here's the graph of f, something like that. This is log of x. Now if I want to graph log of x minus 1, I need to use my transformations to do that. So what I've done, if f of x was log x, then log of x minus 1 is the same as f of x minus 1. Because I took the original function and instead of putting x, I put x minus 1. So what is this? It's a transformation, and we shift to the right by 1 unit. So let's go ahead and graph that one. So each of the points I had before now gets moved over by 1. So we move about 1 in each of these points. So my new graph is going to look something like that. I can use this transformation as well. So if my original function was log of x, and then I add 2 to it, h of x is the same as f of x plus a 2 added on to the end. So I just take each of my original points and shift them up by 2. And so I end up, instead, I still have this horizontal asymptote, but my graph looks more like this. So that's h of x. All right. So it's the same ideas that you've been seeing for transformations before, only now we have to recognize where the shift is happening. Inside of the log means a shift to the left or right. Outside of the log means a shift up or down. This idea can also help us to understand the domains of different log functions. So ln is just the log base e, remember that. So what I'm looking for is my function is log base e of x minus 2. So note that the domain of ln is just all x values greater than 0. So what this tells me is that x minus 2 now has to be greater than 0, because that's what I'm plugging into the ln function. In other words, x must be greater than 2. Another way that we could see this is if I graph just the ln function, that's going to have, it's going to look something like this, where I have my vertical asymptote at 0 and my x-intercept at 1, 0. By switching x to x minus 2, so this one was ln of x minus 2 is going to be shifted right by 2. So my new x-intercept will be here, and the horizontal asymptote that I had before is now going to be at 2 because the asymptote will also shift right. So the graph will look something like this. And you can see now that the domain is all the x values bigger than 2 because the asymptote shifted. I'm not going to get anything over there. Let's do another example. ln of x squared. Well, we know that what we plug into the ln function has to be bigger than or equal to, has to be bigger than 0. So the only thing, we're squaring this function. So no matter what we plug in, it's going to be bigger than 0 unless we plug in 0. So the domain of this function is just all reals except 0. And it turns out that the graph of this thing looks something like this. And we can double check that in our graphing calculator by using the ln function, ln of x, and looking at the graph. Oops, let's go to a normal zoom, standard zoom. Oh, sorry, I wanted ln of x squared. That's why we got the wrong graph. And so now we see both pieces appearing, and there's that vertical asymptote right along the line x equals 0. Okay, so the transformations help us to see where the vertical asymptote shifts. Here we didn't shift left or right, so we still had a vertical asymptote at y equals 0. And since we were squaring, everything we'd be plugging into this would be positive otherwise. So all we have to leave out is 0. In this example, we shifted to the right by 2, and so the domain also shifted to the right by 2. Instead of being x bigger than 0, it became x bigger than 2 as our domain. So I hope that this gives you some intuition for how to graph these transformed logarithmic functions and how to find the domains of them. Please let me know if you have any questions.